Okay, welcome everybody to today's California Dreams technical seminar. We are very lucky to have with us today Professor Sudhakar Pumarti from UCLA, where he's a professor of electrical and computer engineering. He did his bachelor's at IIT and PhD in electrical engineering at UCSD before deciding to stay within the hub well before the hub was formed and coming to UCLA. He has worked with or consulted with software and hardware companies on wireless, wireline communications, IC design, with a research focus in developing circuit and algorithmic techniques to overcome common impairments in integrated circuits. He serves on editorial boards and technical steering committees of the key journals and conferences in the IEEE Solid State Circuits and Circuits and Systems Society. We're very glad to have Sudhakar with us today. Sudhakar, please feel free to take it away.
Well, thank you, Steve. I'm happy to be here, giving you all an overview of what we at UCLA ECE specifically have been working the last few years. We've been looking at the data access, the data movement problem in AI hardware, right? So let me share what we've been doing on this thing. This is somewhat of an overview talk, so I'm not going to go too deep into any one particular topic. The idea is just give you an idea as to what all the various things we've been doing. So before anything else, please note that this is a large collaborative piece of work. It's several people, mostly me working with four of my colleagues, Professor Kang Wang, Professor Puneet Gupta, Professor Ken Yang, Professor Subbu Iyer, and their groups. The work is obviously done by the students. Here is a list of students from different groups who've been working on this thing over the years, multiple PhDs, master students, some of them are still working on and so on. The bulk of this work has been funded by DARPA through several programs, FRANC, later on LTLT and OPTIMA currently. The technology that came out of DARPA FRANC, we later worked with Northrop Grumman as part of the ERIDA thing to try to see how practical it is and so on. Along the way, we got additional support from, say, Qualcomm Innovation Fellowship. So some of our students, some of the things, Intel and Global Foundries provided some partial tape-out support here and there. And that's basically the contributions and support. So let me get to the actual details. Okay. So let me talk about the data access movement problem. I'm sure most of you are familiar with this thing, but just to set the stage. So the primary problem with modern AI, ML, is that the models are very, very large. Even simple models working on edge devices are also very large. The amount of compute required and the amount of data required, memory weights and whatnot required is growing literally exponentially. And so what is the problem? So typically what happens is these models are so large that they can't fit on the chip. So usually they are off the chip, sometimes in DRAM, sometimes in hard disks, and then they have to be moved from there to the processors. And on the processors, they do the computations and the results have to be moved back into this thing. So bottom line, there's a lot of data movement and data access. And it turns out that the cost of reading data and moving data is far more than actually doing the computation. So for example, if you look at the figure on the bottom right, moving or reading a 32-bit word is roughly an order more than reading a 32-bit word from SRAM. So DRAM access is about 10 times more than SRAM access and moving it. And then that is another order more than just computing it. So what's happening is that the total energy consumption and the latency of these systems is overwhelmingly dependent on data access and movement. Okay, so that is the theme that we have been trying to address. So what have we been doing? Let me, from a high level point of view, our summaries like contributions are like this. This is obviously not a simple problem. It's a fairly challenging, multi-dimensional problem. So we've been trying to attack it from different points of view. So number one, we have developed high density CMOS integrated voltage controlled magnetic memory. So the idea is that if you have very high density memory that sits right on top of the CMOS chip, then you don't have to move the data off the chip from the DRAM. So that will substantially cut down the largest portion of this power consumption, the energy consumption, the DRAM read thing. So that's something we have done. Next up, what we did is we've been looking at compute in memory. Let us say you have such high density memory. We've been trying to look at how we can do many of these ML computations within the memory itself. So normally you will move both weights and data from wherever they are stored to a processing element, and there the computation is done, and then you move them back. So that's a lot of data movement. So in computed memory, the idea is that you can keep, let's say, one of the set of operands, let's say the weights sitting there. That way you cut down half the data movement costs, right? And if you have a high density memory, then you can pack a lot of weights. So this way we can cut down the data movement on the chip itself. So we've been doing some work there. Then we've been looking at some architectural improvements, stochastic computing, new paradigms of computation. The idea here is to make the core compute element extremely small. So if you make the core compute element extremely small, then you can pack your chip with thousands of those things. That way, when you bring data from off chip or wherever, then you can reuse it quite extensively before you have to move it back out and get something else. And this is not a new trend. Like if you think about it, we started with CPUs, then we went to multi-core processors and GPUs and ASICs with many, many processing elements. So this is along the trend, but stochastic computing takes it to kind of an extreme where we pack like tens of thousands of compute units on a single chip. And finally, all of these techniques, at the end of the day, you still have to move data, especially a lot of it on the chip. And we came up with the interesting techniques to improve the efficiency and the throughput of communications on the chip. And some of those techniques can also be applied for on substrate. So these are this is a multi-pronged approach that we've taken to address this whole data access and movement problem. So let me get into these things one by one. So let me start off with the first one, the high density voltage controlled memory, right? So first of all, why do we need these high density memories? So here is a typical various memory hierarchy stuff. So you have these very dense memories like magnetic memory, disk drives, NAND flash, and so on, DRAMs. They're usually slower. Some of them are non-volatile. They sit usually off the chip. And then you have these much faster memories, SRAMs, register files, and so on, which are not as dense, take up a lot of space, and they sit closer to the processing elements, right? So what we want is we want some of the denser memories very close to the processing elements, which means we want much denser memory replacing or augmenting the SRAM. Now, with technology, the logic is scaling very well, at least till now, but the SRAM scaling has not been that good, right? And this is what many of the foundries are observing. So that is not helping that much. Other folks have tried to embed the DRAM. So rather than have a DRAM off the chip, they have a variety which is embedding onto the logic chip itself. That has some success, but DRAM needs a lot of refresh, which has energy costs and latency costs and so on. So bottom line, there is a need for the strong high density, there is need for high density CMOS integrated memories that don't need a refresh, right? So that is the motivation. And a lot of people have worked on this thing. There are many, many variants of this thing, many approaches to this thing. I'm listing just some of the more popular ones. There is the PC RAM and the ReRAM. Those are resistive kinds. And then there are the magnetic variety, STT RAM. The stuff in the green, the last column, that is what our contribution is. Basically, what we have done is we have done a variant of the magnetic memory. But unlike STT-MRAM, this is controlled, the switching is controlled by an applied electric field. Okay. So as you can see, our memory, and I'll show you shortly, this is much denser than the other memories, about 2x, 3x denser. The switching times are at least an order faster, and the switching currents are about at least half an order or so better. So that means the write energy, write speed is very, very good, right? The write voltage is also very low. Endurance is very high. It's a non-volatile thing. And what we have done is we basically actually demonstrated this integrated. This is the first CMOS integration. So a lot of groups out there working on individual devices, but we took the trouble to actually integrate them on top of CMOS wafers to show that this is actually viable. So let me explain briefly what this is about. So the core device is a magnetic tunneling junction like the STT-MRAM, but there are some differences. In the STT-MRAM, a current flowing through, so like in STT-MRAM, you basically have a MGO layer that is sandwiched between two magnetization layers. One of the layers is fixed, the other one is a fixed magnetization, the other one is free. In STT-MRAM, you pass a current, and that current will basically change the magnetization in the free layer to be either parallel with the fixed layer magnetization or anti-parallel. In our case, the device is similar, but the MGO layer is thicker. So that means the resistance, tunneling resistance is larger. And the switching mechanism is not through current, but through voltage. So we apply a field. Then what happens is that because of a voltage controlled magnetic anisotropy effect, the magnetization in the free layer, it goes through a precession of roughly about a nanosecond period, 1.2 nanosecond period. So if you time it and you remove the applied pulse at half the period, then you can cause the magnetization to flip state from parallel to anti-parallel or vice versa, right? So that is the basic idea. So it's very fast because it is only about a half a period, or it's about 0.6 nanoseconds or so switching, so very fast switching. And the write energy is very low because you're not using a high current to switch it. You are using this voltage, right? So that is the basic idea. That is what makes it advantageous compared to STT and TTL. So top left is basically showing this core device. So it's basically a one transistor, one MTJ device. What we have done is we have built memory peripheral circuitry on 0.18 micron CMOS from TSMC. And then we went to E3 in Taiwan, and they manufactured arrays of these devices on top of them. And then we bonded them together, the entire, not together, it's back end. So then we took that whole thing, boiled onto a PCB, and then we did array measurement. So we measured up to 64 kilobits. So this is a fairly reasonable size memory. And what we found is that this is 6 times denser than SRAM, but it has comparable speed and energy. And compared to STT-MRAM, basically it has much, much lower, compared to the other non-volatile memories, it has much, much lower write energy and write latency. So we did several measurements on this thing. I'm only showing you a sampling of the measurements. So here, all 3 chips tested. Figure on the top right is basically showing the switching probability as you increase the pulse width. If the pulse width is set right, then it actually switches very nicely and so on. We have written them, small arrays, big arrays, and so on. Bottom line, we did this thing in 0.18 micron CMOS only because E3 needed an entire wafer to process it. And getting a wafer in a finer node costs about a couple of $1 million, which as a university we cannot afford. Given that these are CA dreams, at that point at least, we seriously sorry about the fact that we had to go all the way to Taiwan to get this kind of an integration facility. We just couldn't do it anywhere in the US. Perhaps CA Dreams or any of these things will facilitate this kind of work in the future, or any of these ME Commons centers or whatever. That I think would be very, very useful. Anyway, so coming back to the story, so we demonstrated a magnetic memory. This is much, 6 times denser than it's a 1T, 1 MTJ device. It is similar performance as SRAM, much denser, and much lower energy than STT-MRAM. So this, I think, is very viable. Now we are trying to find some partners that can take this thing to a more advanced CMOS node and then show that this is actually very useful, right? So that's the first thing that we worked on. Any questions on this thing before I move on to the next contribution? Okay, so if there are no questions, let me move on. So next up, compute in memory, in high density memories, right? So like I mentioned previously, compute in memory can cut down costs. So we wanted to see how we can do in high density memories. So before I get into exactly our contribution, let me briefly talk about what the why we need compute in memory, what are the issues and so on, right? So at a very high level, why do you want to do compute in memory? So the idea is that if you have a memory array, typically you store the weights there. In another memory array, you store the inputs or activations, and then you read them both, go to logic, multiply, add, and whatnot, and then put them back. In computed memory, on the other hand, you would do something like the following. Let's say you put the weight vectors already in the memory, sit there, they reside there. You stream in the input vectors from another memory, and then multiple rows of the memory are simultaneously activated. And now both the weight vectors and the input vectors are all simultaneously available. So you do the dot product computation. Now that computation can be done in analog or digital. But the main point is that you are not reading the weights one by one from a memory. Memory read is expensive because you have a very long bit line with a large capacitance. And when you read them one by one, it takes up a lot of time and energy. So that is what you are really avoiding. That's where the fundamental savings of computing memory come from. It's not a magic bullet. It will roughly save half the overall cost because you are only storing one set of operands, let's say the weights. The inputs still have to be moved, right? But that's the main benefit. Now, like I said, the dot product computation can be done in analog or digital. So when people do the computation in digital, we call that digital computing memory. Basically, what it means is that you are reading out the arrays in parallel. It is like a very wide memory, basically. And then you have digital adder trees and some other logic, right? So these adder trees grow exponentially with number of bits. So usually beyond 6-bit compute or so, that can be very large. But people have been trying to do this thing. The adder trees scale very well with technology. But the problem is that the cells, the SRAM cells where the weights are stored, they don't scale very well. So that's the problem with the digital CIM. Now, alternative is analog CIM. So here, the computation is not done using adder trees and so on. Here, the computation is done either in the voltage, current, charge, or time domain based on individual preferences and so on. So for example, if in a memory array, if you, let's say, figure at top left is showing you a memory cell, and then these two transistors in red, they realize an AND operation, like a product of 1-bit weight and a 1-bit input. And then that draws a current from this CL line. So all the current from different rows will all add up, and that represents the dot product in current. And then you pass it on to an analog digital converter, and then that gives you bits. So this one promises a very high energy efficiency because you're doing multiple computations all in like one go, and also promises very low latency. So a lot of researchers, university researchers, also startups have been working on this thing for a while now. There are many challenges. That's generally the case. A lot of promise, a lot of challenges, right? One of the main, a few of the main challenges are the following. Number one, the SRAM has poor memory density. You need about 6 to 8 transistors just to store 1 bit, right? So the memory array is still pretty large. That means the wires have a lot of capacitance and so on. So, number two, the analog digital converters that digitize the dot product, they usually dominate the area and energy costs. For anybody in the audience who is an analog designer, if you have built an ADC, you know it's a fairly complicated task, even if it's an 8-bit ADC. That's one ADC. But in a scenario like this, every column, every bit line in the memory array has its own ADC. That's a lot of ADCs, and getting them to work over process voltage and temperature in the presence of mismatches and variability is basically a nightmare. And I'm an analog designer and I know, right? It's a nightmare. Even if you manage to pull it off, the area and energy is too high. Finally, the weights and the compute, they are not accurate because they're all represented in analog quantities with mismatches and PVT variations. It's not accurate. Right? So these are the many problems that are plaguing analog CIM, but because of the potential, people are still looking at them. Right? So let's look at the first one, the SRAM and poor memory density thing. To avoid that or to get over that, what people have done is they have tried to do compute in memory in a high density memory. So for example, compute in memory in MRAM, right? MRAM is very high density. It's only one transistor, one MTJ per device. But they have tried to do it in embedded DRAM or eFlash and so on as well, right? What we try to do is we try to do it in our own version of the MRAM, which is the magnetoelectric RAM, the voltage controlled MRAM that I previously described. So compared to the SRAM, this memory is far denser, like 5 times denser, right? Read energy and read latency are similar. It is non-volatile, right? So this is very promising. Some of the other technologies like EDRAM and STT-MRAM are also very promising. So all of these things are promising because they address this SRAM has poor memory density problem. But they present other challenges. So number one, they are non-volatile, right? And they are not available as logic values. They are stored as the magnetization in an MTJ or the resistance of some device or things like that, right? So let's take a closer look at these problems. So again, there are many challenges, but there are two main challenges. So let's consider a simple case, right, of an MRAM. So there is a one transistor and there is a device, the MTJ. Depending on whether the device is in the on state or off state, it behaves like a resistance with a different value, right? So RP and RAP, parallel and anti-parallel. Now, the resistances, ideally you would want them to be like some small value and a very large value, but in reality, their ratio is only about 2 or some small number like that. We call this a low TMR or a low on-off ratio. By itself, that's not a problem, but when you have variability and mismatches thrown in, when you compute the dot product, because the ratio of an on and off is very small, the dot product is very difficult to compute the dot product reliably, right? So the figure on the right, it kind of characterizes, given device mismatch sigma, how long a dot product you can realize reliably with technologies with different on-off ratios. So if your device for a capacitor, for example, where you charge some charge or show some charge or don't store some charge, then the ratio is like very large, and you can realize dot products up to 1,000 or 2,000 long, right? That's many of the SRAM switch capacitor CIM people are doing. But if you do something like RAM or STT-MRAM or something like, or even our own MERAM, you usually can get only about dot product lengths of 10 or something small like 20. Then it is not very efficient. The ADC costs are not amortized well and you have very high costs. That's one problem. The second problem is that if you usually you want to use a weight multiple times, right? You want to use a weight for multiple dot product computation with different inputs. So this weight bit is stored as a resistance or a magnetization. So if I want to reuse it, every time I want to reuse it, I need to read it again. Basically, for example, throw some current through it. That leads to poor efficiency. So these are the two main problems, right? So we wanted to get around that thing. So we developed a technique, and I'm going to describe it in the context of our voltage controlled MRAM, but it should be extendable to other non-volatile memories, high density memories as well. The idea is that we have a very compact magnetic to digital converter or MDC. Basically, that takes bits stored in this magnetic domain and then converts them into logical bits. It's a very small, it's like a compact magnetic digital converter sitting inside each row. So it will read these bits one by one in a time interleaved manner. And once the bits are available, you can use them to either do digital CIM or analog CIM as what is your preference or dictated by other considerations. Obviously, the key is how can you get a very, very small compact circuit that can fit within a row of the memory array. So we designed a circuit. It's only a 6-transistor circuit. It actually employs local offset calibration, which is stored on this calibration cap, right? And basically, it simply takes that thing and converts to a logic bit. And this thing in 28 nanometer consumes about only 2.6 femtojoules and is very fast. It only takes about 0.5 nanosecond, right? So that's basically what we put in. So with that, now that the logic bit is available, I can reuse the same bit in many, many different dot products. So I'm reusing as well. So this way I solve both the problems. Once the logic bit is available, now I'm not concerned about the low on-off ratio of this thing, right? So it enables high weight reuse and accurate CIM and is not limited by the on-off ratio. And it can be used in analog CIM or digital CIM. So we went ahead and we kind of designed a system based on this thing, and we simulated basically what kind of efficiency we can get and so on. I don't want to bore you with the actual details, but I'm comparing this with a lot of other state-of-the-art CIM in non-volatile high-density memories, RRAM, STT-MRAM, and also SRAM CIM. The conclusion is that in 28 nanometer, we are about, compared to STT-MRAM, we have 4 times better area efficiency, TOPS per millimeter square, and we have comparable energy performance. Compared to SRAM, we are 2 times energy efficient and comparable area efficiency. So suddenly what I have is I have a high density memory and I can do CIM in this. Okay, so that is computed memory with one kind of high density memory. It is high density simply because it's a 1T1 MTJ structure that stores 1 bit. Next up, we looked into computed memory with charge trap transistors, right? So what is a charge trap transistor? Basically, it's a core device, let's say in a FDSOI process. And we have a mechanism by which we can change the threshold voltage of this transistor very precisely, very finely, and it is in a non-volatile manner. So suddenly, we can store up to about 6 bits in a single transistor, right? So, which means that this is about 20 to 40 times more dense than an SRAM, substantially higher density. Also, it doesn't need any additional mask steps like the STT-MRAMs or the other EDRAMs and all of those things. Read energy, read latency is very, very good because this is like a regular transistor, right? And so on. The one issue is that you cannot write it again multiple times, but I'll talk about that later, right? So that is the device. So let me briefly, that suddenly opens up a lot of possibilities because you can store a lot of bits in a single transistor and I can do CIM a lot more efficiently. So let me briefly talk about a device. So it's like I said, a core device and an FDSO technology, high K gate. So the idea is that you can trap some charges at the boundary, right, of this high K gate. And that charging mechanism is helped by self-heating in the device, right? But from a circuit or a user point of view, if you let some current flow through the device, through the channel, and if you apply a reasonably high gate stress, then you can shift the VT of the device. You can increase it, and it is non-volatile. The shift stays there. You can also erase it by applying no current in the channel and then applying negative gate stress by about minus 0.8 volt or something. And for the positive stress is about 2 or 2.5 volt or something. So this way you can change the VT, and you can change the VT by about 250 millivolts, and it is continuously programmable and you can get very, very fine resolution. Right? This is in Global Foundries 22 FDX is what I'm showing you here. We have also seen the behavior in 12LP, which is a FinFET process and not FDSOI. We have also seen this behavior in TSMC 16FF. So this behavior seems to be prevalent in most of the high gate systems. Okay. So what have we done? So we taped out a bunch of devices. We measured individual devices as well as devices in an array, and we were able to show up to 6 bits programmability in a fairly reliable manner. The figure on the left is showing the programmed current and the measured current. That is up to 6-bit level in a single device. Figure on the right is showing the same thing where you have an array of devices where we programmed each device in the array to a different value. And we measured the currents, and we saw that definitely we can do better than 4-bit, and in some cases 5-bit, sometimes 6 bits also, but definitely 4-bit. Right? So this is very, very promising. Now, what does that do? I have very high density, and I can do my analog CIM. So each transistor stores like 4 or 5 or 6 bits now. So my dot product computation can happen much faster, much more efficiently, and so on. We found another use for this. I mentioned previously that in CIM, the analog to digital converters dominate performance. Like for example, this is a breakdown, top left figure is a breakdown of the energy in a typical analog CIM. As you can see, the ADC is about 40–45% of the energy. Area is also similarly dominated by the ADC. So what analog CIM people do is they amortize the ADC cost over very, very long columns, 1,000 long, 2,000 long, and so on. And then they report very high tops per watt, tops per millimeter square numbers. But then systems people, they can't really use them because many of the networks don't need that long dot products. So the real system performance is terrible, even though the CIM reports a very high peak efficiency. That's a big problem. But anyway, what you want is you want ADCs that have very low energy, very low area, and you want them to be fast. Why fast? If they're very fast, you can multiplex them between multiple dot products. That way also you can cut down area, right? So figure on the right, what we did is we took state-of-the-art ADCs in ISSC, VLSI, and so on, JSSC. X-axis is energy in picojoules. Y-axis is area divided by the sampling rate. And we want to be at the bottom left corner of this plot that has low energy, low area, and high speed. These are various ADCs reported, showing different SNDR performance, different technologies, and so on. We want to be at the bottom left. And this small light bluish rhombus, that is what we have been able to achieve using CTTs. I'll describe that thing shortly. But because we have this charge trap transistor whose VT I can adjust precisely, we figured out a way to use that thing and get this really, really efficient. In fact, we've tested it, taped it out, tested it, and this is the most compact and the lowest energy 8-bit ADC reported up to 22 nanometer nodes. It's only 8 micron by 75 micron. That's about 4x smaller than anything else out there. And only 5 femtojoule per conversion step. So what's the big deal? What's the big idea here? Idea is very simple. ADCs, for example, most of the ADCs used in CIM or SAR ADCs, and SAR ADCs have DACs. These DACs have mismatches, and the mismatches affect the performance. So to minimize mismatches, people will use large devices, but large devices have large parasitics, so this slows them down, or you have to burn more energy power. Or they have to do calibration, and the calibration information has to be stored in flip-flops. And flip-flops are big. About a flip-flop is about 20-odd transistors, right? What we do is we use minimum size transistors in the DAC. It's a current DAC, minimum size transistors. They will have mismatches, but we adjust the VT once to tune out the mismatches. That way I can get away with minimum size devices, so I get very low parasitics, high speed. That initial adjustment, that's my calibration. But because the adjustment of the VT is non-volatile, it stays there. It is remembered forever. So I don't need flip-flops to store this thing. So it's a simple concept, but that's basically what we did. So figure on the right is showing you a block diagram. Looks very complicated, but the focus is on the red block inside. The blue devices are the charge trap transistors. They make up a current DAC, and we made sure that we can program them. right? Programming requires high voltage, negative voltage stress. So we included all of the circuitry on the chip, and then we tested this thing out. So top left is the layout, very compact. It's only 8 micron by 75 micron because the DAC is very small and there are no flip-flops to store calibration information. Anyway, we tested this thing out. Here is a sampling of the measurement results. Figure on the left is basically plotting relative error in the DACs. The blue curve is without the VT adjustment, very large errors. So up to about 80% errors, as you can imagine, because these are minimum size devices. And the orange ones are after the VT calibration. So they are like less than 7%. Not only that, we programmed them at room temperature, calibrated, and then we measured at 80 degrees as well as minus 40. So not only is it non-volatile, it retains well over temperature stress and so on. So this is going to work over PVT. Figure on the right is basically showing DNL and INL before and after the calibration. You can see there's a huge improvement because of this. So we did other measurements also, but I'm not showing you the thing here. But the main point, like I said, is it is the lowest energy and the most compact CDT-based ADC out there, already measured. So now that we have these very high density CDTs, which can store up to 4 bits to 6 bits in an individual transistor, and then I have a CTT-based ADC, which is very, very compact, we have designed a CIM based on this thing. So you have columns, columns of CDT storing the weight vectors. We apply inputs on the gates, and then the currents are mirrored and then sent to a CDT-based ADC, right? And we designed basically an 8-bit input, 8-bit weight, 8-bit output CDT, CIM. And that will give us about 100 tops per watt, 25 tops per millimeter square, and an incredible almost a half a megabyte per millimeter square weight density, all in 22 FDX. Right? Just to give you an idea, this is better performance than state of the art in digital and analog CIM in much finer nodes like 7 nanometer and 5 nanometer. Now, of course, this thing is not measured yet. It is still IC in the foundry, but these are all similar results. But like I said, we have already verified the CDT ADC in the same technology. That is already very measured. And the fact that CDTs can store multiple bits and you can do a dot product, that we taped out a previous chip in 22 FDX and measured that thing also. So we are very hopeful of getting these numbers. Like I said, that the CTTs, you cannot write them again and again. It's very expensive. Write endurance is not very high. But we believe that this can be very, very useful in scenarios where the weights are stationary. So that could be, for example, image processing or radar processing, right? Oftentimes you do a fixed set of, for example, DFTs or some kind of transforms on this data, right? So there you can have a CTT-based CIM like this where the DFT coefficients or whatever are programmed in, and then this offers very high throughput, very low energy processing. You can also do vision transformers for this thing. So we looked at that thing. Vision transformers are very popular these days and finding use in a lot of different scenarios. So the idea is that in a vision transformer, the bulk of the processing, it's done in weight stationary macro, CIM, right? So what I'm saying is not all of the processing in a vision transformer uses fixed weights, but the bulk of it. So for short token length, up to around 200 tokens or what, about 90% or more of the processing is done with fixed weights. So that part we can map to a CDT-based CIM and do it with extreme efficiency. The rest of it, that we can do it simply in a standard digital logic. Could be either on the same chip as the CTT CIM, or it could be on a different chip. The data between the CIM blocks and the rest of it, that's also not very high, only in a few gigabytes per second. So even that cost will not be very big. So what you can do is you can take this kind of chip or chips and you can have tile many of them and simply scale to large systems. We believe this kind of an approach will be particularly interesting and useful to many of the defense applications where they are doing imaging of, let's say, pixel arrays and all kinds of things, right? So we did an estimate as to what kind of performance we can get, right? First of all, in these vision transformer applications, CIM at int 8 level, 8-bit level is good enough for the inference accuracy. You can make the rest of the digits be more accurate, right? The accuracy drop is minimal, is what we have seen. So we compare different systems in this table at the bottom. The bottom 3 rows are different ways of doing it. The bottommost row is using an NVIDIA GPU-based system, right? The one above that is using IBM's PCM-based unrolled network, large network. And the one above that thing is a digital ASIC, T-Rex, right? These are 5 nanometer, 14, and 16. Our 2 rows in green, there are a CTT CIM and the digital in the same shape and a different shape. So if you use, so each chip, let's say a 7 millimeter square chip, basically gives us about, 60 TOPS. Consumes only about 1.8 watts, right? And if you tile, let's say 12 of these chips, suddenly you can hit close to 800 TOPS, right? So this is substantially better than these prior systems. If you look at the NVIDIA thing, you can get to more TOPS by packing more of these things, but the power consumption is 1,000 watts in that thing. The ASIC will have a lot less power, but the TOPS is very, very low because it is optimized to do this kind of a thing, right? So we believe that CTT CIM can be very useful in this kind of systems. Okay. Now let me switch.
Can I interrupt with the question?
Yes, please.
The NVIDIA chip is labeled theoretical, but it's a real chip. Is that because you're estimating based on the characteristics of the chip, or can you explain that?
Yes, it is. Good question. So what I mean theoretical is we are assuming their theoretical peak efficiency numbers. So in a real world, they are not going to hit their theoretical max. So we are being conservative.
Got it.
Does it answer your question? Yeah.
Yep. Very well. Thanks.
Okay. So next up, let me switch gears and move on to something else called stochastic computing. So what is stochastic computing? A lot of people don't know these things. So let me briefly describe it. The idea is that we represent numbers as a fraction of ones in a random binary stream. So let's say you want a value 3 by 8, right? In a typical binary fashion, you may represent it as 0, 1, 1, right? The value is going between 0 and 1, and that's 3 by 8. In a stochastic form, you will have a sequence that is 8 long, for example, and only 3 of the bits are ones. That's 3 by 8. And that's a random stream. The ones could be anywhere. Why does this matter? With this kind of representation, multiplication can be realized by just a single AND gate. You can do the math for yourself. Basically, the probability of A and B is the probability of A times the probability of B. You can approximate addition by doing a simple OR gate, or you can do scaled addition by doing a simply a mux. Bottom line, what I'm saying is that you can realize a MAC, the core operation in ML, multiply and add. You can realize that thing with an extremely tiny gates. So if you had an 8-bit fixed point MAC that says the big, the SC MAC would be about 250 times smaller. Now it's not for free. What we are doing is we are going to use the same gates again and again in time to generate the bits of a long stream, right? Now, obviously, if you want an 8-bit accuracy, you need a long stream, maybe about 256 long, right? So that is not very good. So beyond about 8-bit or so, this thing is not very useful. But sub 8-bit, this is very attractive. So we believe this will find a use in many of the edge applications. Now, why does it help to have a very, very small stochastic MAC? So if you have a very small stochastic MAC, then you can fill your chip with thousands of MACs. So for example, in GF14, which is like a variant of GF12, we were able to get about 90,000 MACs per millimeter square. This is unbelievable density. So how can you use that many MACs? Once you get weights or operands from off the chip, then you can reuse them extensively so that you don't have to read them back again from off the chip. So this basically dramatically cuts down data movement from off-chip DRAM and even from on-chip SRAM, right? So overall, the energy improvement is not that much from a fixed point implementation, but the latency improvements what we saw are about 30x or so. Huge latency improvements, right? And we have designed chips on this thing, taped them out and measured them. EDP improvements are at least 2 orders, or about 2 orders compared to Iris, which is from Professor Vivian Z's group at MIT from a while ago. Or that thing. We also showed that even though we have a weird representation, we are still able to train it properly, and we are able to get inference accuracy compared to 8-bit fixed point only using 64 long streams, right? So this is very promising for edge applications. Now it gets even better. I can actually do this stochastic computing Mac in memory. So for example, let's say this is a bit representing the stochastic sequence, and let us say this is an input bit. These two AND transistors are an AND operation. And this wire, that's a wired OR operation. And this sensam gives me 1 bit. So that basically does this MAC and OR again and again and again. So this thing, basically, I can embed this thing. Now, what do? I have outside the array blocks that generate the stochastic sequences for the inputs. Inside the array, in fact, inside each row, I will embed a local, very, very compact sequence generator that takes binary fixed point SRAM weight stored in SRAM cells and locally convert them and generate a long enough stochastic number sequence. And then we do this thing, and then that's it. Now you see that the structure is very similar to a regular CIM, but with a big difference. There are no ADCs, there are no DACs, because I'm only doing a 1-bit decision. This is very much like a memory structure. I basically have a sensam here. So suddenly, all the problems of the analog CIM are gone. I don't want to build ADCs, that many ADCs. I don't have ADCs. The energy cost is substantially lower. Now, obviously, if you want like 10-bit, 12-bit, then you need to run this thing again and again over a very long time, and then you start losing the benefits. But sub 8-bit, we have shown that this thing offers much better energy consumption and far lower latency than other systems. So we took this thing and we, let me skip this detail of how we generate the stochastic sequence for now. We took this approach and we actually built an accelerator for object tracking, right? This accelerator can handle both frames, image frames, or also from event-driven frames, right? So we are assuming 6-bit frames. We'll do 6-bit weights and 6-bit outputs, or for if it's an event-driven, it's a 2-bit input, again 6-bit weight and 6-bit outputs, right? It will do this processing. So for the frame-based data, we can get about 86 tops per watt, and for the event-based data, we can get up to 500 tops per watt, right? And the system throughput is very large, especially when you're processing events. We can go up to 500 million events per second. So that is in GF12. So imagine a typical setup. So if you want to do object tracking, there's a bunch of things. The bulk of the processing is done in these convolutional tracking filters. So that is what we accelerated on the chip with our stochastic computing based accelerator. And the rest of it, we did it off chip, right? It's about 80% of the cost. So we take a 480 by 640 frame, we take regions of interest, and we apply different Gabor filters. And then we run subsequent processing, and the point was to basically track moving objects in this thing. This was done in collaboration with Northrop Grumman as part of the DARPA FRANC. So let me show you a quick video. So this is basically a bird data set, basically a data set, a video of flying objects, right? And this is processing the whole thing, and we are tracking birds. Those orange and green boxes are identifying where those birds are, right? So you can imagine this kind of thing being useful in many applications in industrial automation, defense, and so on and so forth, right? So measurement comparison table, but I don't want to bore you with the details. But the main point is that this thing is the highest reported throughput and throughput density in event camera data processing. So we are able to handle about 500 million events, whereas prior art is only able to handle about 11 million events or so, right? This, I think, is a huge step in handling those kind of problems. So let me quickly get to my last topic, efficient data communications, right? So we've been so far talking about how to cut down data movement, right? We've been doing different things to cut down data movement, but at the end of the day, you still have to move data, right? And that problem is there. And that problem is becoming really, really problematic, right? Students ask me, and circuit design student, I tell them that with AI, the demand for circuit design students is actually going up, provided they're doing either clocking design or IO design because of this problem. So basically what's happening is that you are ending up with these multi-core systems, large SoCs with multiple cores or hundreds of processing elements, or you have these much larger systems like these Cerebras, wafer scale systems, and so on, where you have many, many cores, and the compute is distributed everywhere, and your overall system performance depends heavily on data movement back and forth, right? So you want very high data throughput, and you want very low energy, very high energy efficiency. Also, many problems want the available bandwidth from one particular processing element to another processing element. They want it to be very programmable, preferably dynamically. Sometimes I want to send only less data. Other times I want to send a lot of data. Maybe I want to broadcast or things like that. Traditional networks is very difficult to do with these kind of things. They overlay networks on top of underlying hardware physical layers. So we looked at this thing. So let's say on-chip communication. What's the main problem? On-chip communication, unlike chip-to-chip communication with over PCBs, on-chip communication is limited by bandwidth per cross-sectional area. So the tendency to run links faster doesn't help here. Why? If you run faster, the losses go up. So your transmitters and receivers have to become very, very complicated. So they take up space. So the bandwidth per cross-section again drops, right? So that's not very good. Still, people have tried to do fairly complicated multi-level signaling. Here is simply an 8-PAM that I'm showing. People have also tried even more sophisticated OFDM-like things, especially between two dies on the same substrate separated by only hundreds of microns or a few millimeters or so, right? Again, the issue is that for this kind of thing, the circuitry is very, very complicated, as you can imagine, right? Anybody who does SerDes design knows that the circuits are very complicated. On chip, generally, when you have only binary signaling, what you do is you simply buffer the links and you leave it to a tool to figure out where to place the buffers and so on and so forth. So what we set out to do is we wanted to do multi-level signaling, but we wanted to do simple buffers. If you do analog buffers are not at all efficient. So we came up with a solution. These are multi-level buffered solution. It's actually very simple. What you do is you get your received multi-level signal. You put a very compact ADC. Let's say it's eight levels. So you have an 8 ADC, 3-bit ADC. And then you launch it back onto the line, to the wire, but using multiple switches connected to different supplies. Because these switches are connected to different supplies, this is a very efficient class D kind of drive. That's efficient. So the only real cost is the ADC. Right? Now you require clocks for this thing. You need voltage regulators to get all these various supplies and all of those things. But you're going to have many, many such links. So the cost is easily amortized over all of those links. So that's not a problem. Right? So here is a very quick look at what our technique looks like. So you basically have 7 comparators. The comparator is a very, very small comparator, offset canceling comparator, 6 micron by 1.3 micron, tiny, and consumes only 36 microwatts at 4 gigahertz. This is in Intel 16, I believe. Right? Low offset, low noise. And we just have 7 of them. That gives us 7 bits. And then we have simple inverters, whatnot, to drive switches here. That's all. Right? So this approach actually allows us to do really interesting things because each buffer is digitizing locally and relaunching the signal. What you could do is you could take the data and you can modify the digital data however you want. So for example, you can realize time division multiple access or code division multiple access. You can do broadcast, you can do any to any node communications, you can do variable bandwidth allocations, and all of those kind of things. You can overlay them very easily simply by changing the digital logic with negligible cost to the overall system. So anyway, we built this thing. We built two prototypes. One is a PAM8 prototype. This is an Intel 22 nanometer FinFET technology. We built a channel M8 with very minimum spacing, close minimum spacing, 0.24 micron spacing only. And we built other prototype which allows us to do CDMA and TDMA. So we had 8 mm long lengths. Every 1 mm or so, we had one of these buffers, right? We had on-chip bit rate monitors and all of that stuff. So let me skip to the main part. We tested CDMA, TDMA, different configurations of sending data from anywhere to anywhere. And here is the main. X-axis is normalized speed. Like I said, it is data rate per cross-section and length. This millimeter is length and this is cross-section. This is energy, so femtojoule per bit per millimeter. So this is various prior art out there, and this is where we are, PAM8, and this is TDMA. CDMA is not as good. It will be somewhere, I believe, out here, I guess. But these two are really good. So suddenly we have a very simple way. And the thing I like the most about this is that you can simply take this block, do this thing in analog by hand, custom, and then you can incorporate this thing in a digital flow, which will just go ahead and place the buffers wherever it wants to on a large chip. You can also do it on die-to-die communication on a substrate, as long as the spacing between the die is maybe only 1 mm or 2 mm or so. So this, I think, is a very viable approach going forward. So in conclusion, so we did a lot of things to address this data movement problem. We showed high-density MRAM. We talked about how to do CIM in high-density memories, right? This is all in collaboration with DARPA FRANC. We showed stochastic computing, and we did multi-level buffered interconnect. That was part of LTLT. And finally, we are working on CTT-based CIM, which is partly done. That is as part of the DARPA OPTIMA program. Any questions?
Pause for a minute to see if we have any questions from the audience. If you have a question, you can raise your hand and we can take you off mute, or you're welcome to put it. I think there should in the Q&A box. While we're waiting, maybe I'll ask, how much is machine learning and AI affecting, how much is it being used in your current design work for circuits, or is it, and how do you see that changing over time in the near future and further in the future?
Yeah, so very good question. So far, at least in our group, we have not been using machine learning to analog circuit design. We have not been doing that part. We have been primarily, we are the other side of the equation. We believe eventually this will spread everywhere in many tasks, and we want to see how we can actually make that one be practical and low energy. But our architectures, many other solutions are simple enough at the circuit level. So I believe it should be possible to do it in the near future. Yeah.
We have questions from others in the audience. I see lots of familiar faces from the hub. If not, we are at the top of the hour. So thank you very much, Sudhakar, for the great presentation. And I think Amy has a few slides she can display as we finish here.
Oh, my pleasure. Thank you.
Yeah, thank you. I hope to see you again sometime soon. Coming up next week, we have David Harami from AIM Photonics. I think this may be the first talk we have being given from outside the hub, although we are partnered with AIM Photonics. And the following week, Alexander Yanta Polinsky from IBM. And I think we have another slide that has our QR code. For those of you who want to subscribe to the series, we do this almost every week, Friday at noon Pacific time. And we will look forward to seeing you. Before I stop, though, there is one question in the Q&A from David Chang at SRI. David, you're welcome to come off of mute if you'd like, or I can read your question.
Yeah, for 2.5D stacking.
Okay, yeah. So one of your slides, you were showing the 2.5D stacking technology. I'm not sure if you have used that technology and what company would you recommend?
Yeah, so we have not used it for the things that we described.
Okay.
But my colleague, Subbu Iyer, who's involved in a bunch of this stuff,
Yeah.
he has a very advanced 2.5D thing that he could do, right? It's still a university thing, but he has a center here at UCLA. He claims we can do sub 10 micron, pitch connections and so on. What we try to do is we try to come up with our techniques to be free of a particular 2.5D technology, but at the same time, like I said, my colleague can do much finer.
Okay.
2.5D if needed.
Is this a mature technology or still in the lab?
He claims it is mature. I can put you in touch with him.
Yeah. Can I send you an email?
Yeah, sure.
Thank you.
Yeah.
Yeah, I think they run a service, so it's kind of in the lab, but it's run as a service, I think.
Okay.
Yeah.
Okay. Good.
Repeatable.
Thank you.
Okay, I think we're out of questions unless somebody else slips one in before we hang up. But thank you again, Sudhakar, very much. It was a great talk, and I look forward to seeing you again soon and watching your work.
Thank you. My pleasure.
Thanks, everybody.